Hello everyone, my name is Jiang. What I am reporting today is a complex neural network adaptive beamforming for multi-channel speech enhancement in 10 domains. First of all, let me introduce what speech enhancement is and the types of speech enhancement. Speech enhancement algorithm is an important technology to process speech in noisy environments to improve speech quality and intelligibility. The types of speech enhancement is mainly divided into single-channel speech enhancement and multi-channel speech enhancement. And according to the types of noise, is mainly divided into stationary noise and non-stationary noise. The common input feature of the neural network model are as follows. The first one is time domain waveform, and the second one is the amplitude spectrum of short-time Fourier transform. And the last one is complex number information after short-time Fourier transform. The simplest input feature is the time domain waveform, a common end-to-end speech enhancement model. Commonly used neural network use the amplitude spectrum of speech short-time Fourier transform as the input feature of the model, and then estimate the amplitude spectrum of the target speech. The phase restored from the speech by using the phase of noisy, and the most typical model is CR model. We know that the phase information has an impact on the quality of speech. So a new model structure is proposed in 2022, which is DCCR model. At the same time, the complex feature of the short-time Fourier transform is directly used as the input of the complex model. The experimental result shows that the model greatly improved the effect of the speech enhancement model. Inspired by the DCCR model, we expect to apply the complex model in the time domain. So we put forward the time domain feature of Hilbert transform processing. At the same time, compared with the previous work, it is found that the proposed method can indeed improve the performance of the speech noise reduction model. The formula of the input signal we use Hilbert transform The Hilbert transform of the time domain were from proposed in this paper, and x tilde and x when represent the two channels respected, where x, kt, skt, and nkt represent noisy speech, clean speech, and noise, respectively. We use Hilbert transform to process the time domain input future, where H indicates Hilbert operator, and now we have both real and imaginary time domain waveform for the proposed network. The structure of our model is as the following picture. We use complex LSTM, which is composed by real LSTM and image LSTM, and then we use this compute method to get the output of complex LSTM. First of all, the CNAB model is to estimate the beamforming filter. It is to attention that the beamforming filter is a complex number. So we use complex linear to get complex output, and then use this complex beamforming filter to convolute with this complex input filter to get the output, and then use CFCNA to process the output of CNAB. The convolution computing method is this, and the output is N out. We also use TCN structure in this model, but note that only the last one dimension convolution block is in the complex network. This read one is the complex compute. The weight of our model is updated by the SISDR loss function. Calculate SISDR from the signal as correct predicted by the model and clean speech. As in SISDR, the numerator is target and the denominator is noise. Obviously, the bigger the SISDR, the better. But in this paper, we have real part and image part. So we need to process all the real part and the image part. And we use lambda to deal with this problem. The lambda is delta 0.5. This is the change of the loss function for the previous work. The result of our model is in table 3. For comparisons, we reproduce CRN and cover testnet and also the MFM-VDR. The cover testnet is a single channel speech enhancement and one channel of our noisy dataset is used for training and test. And the MFM-VDR is trained according to the open source project. This MFM-VDR is also a single channel speech enhancement. The datasets are the same as the cover testnet. The parameter of CRN1 is this, and the CRN2 model size is bigger than CRN1, and also it is the biggest model. Our proposed method has significant improvement, which shows the benefit of multiply channels compared with dual channel CRN. The proposed method also domestic super performance regardless the size of the CRN model. In addition, the influence of interference source in different directions on PSQ. We also analyze the effect of the interference source in the performance of CNAB CFCN model at different mills. High mills, it indicated that the denoising performance is different at different directions, which agree with the concept of traditional beamforming. The influence of complex time domain network on speech quality in terms of PSQ and STR. We study the benefit brought by complex operations. The NABFCN model is the same structure as the proposed CNAB CFCN, but with real operator. The model size of NABFCN and the CNABFCN is shown in the figure 2. Under the same scenario in table 5, it is seen that the proposed complex network outperforms its corresponding real one across all the input SNR Due to the complex operator, the CNAB and CFCN also increase the model size over the NABFCN, which need further compare in real-time application. In this study, we proposed a novel complex time domain means to perform an end-to-end multi-channel speech enhancement network termed as CNAB-CFCN. The Hilbert transform is exploited to generate complex time domain waveform. With the introductions of the complex operation rules, the proposed model outperforms its corresponding real network and other single and dual channel network. In addition, the loss function of SIDR consider both the real part and the imaginary part of the speech waveform to balance the speech quality. In this experiment, we only demonstrated the performance of the proposed network in the case of dual channel, but the extension to more than two channels is straightforward, which is our future work. The end. Thanks for your watching.